And we're recording. All right. So I've been doing a bunch of work lately on the dynamic syllabus here for our course. I think I mentioned a while ago that I haven't taught this course in a while. Actually, last time I taught it, Jim, you took it. It was like 2019, I think it was, last I looked. So it's been, on the order of 5 years since I've taught the course. There just hasn't been an opportunity to teach it. And so, it was a little bit out of date, not a whack relative to my current thinking. And I had switched to Stella and, whatever. And as time permitted, I was changing things, but I had a little more wiggle room here because our undergraduate term ended. And this week we're off quotation fingers. We're just not teaching the kids, but they're back next week. But at any rate, I've made some progress in updating everything and rearranging things a little bit. And I wanted to call your attention to it because I think you'll find it very valuable. So let me say in advance, you're welcome for all the stuff I'm giving you. I wish people would have given this stuff to me, but that's okay. That's my job, is to give you stuff, teach you stuff. But there's good stuff here now. Not that it was bad, but it's updated, refined, rethought, and whatever. Not completely, but we're making good progress in making this a very, very excellent course and site. So I just wanted to review what's on here. We got Sturman's book there.
PDF. Does the link still? The link didn't work when I have it already, but I was just testing all the links. The link didn't seem to work. Maybe it works for you.
Went there.
No, the one, I think the sermon zip link.
So it should, it's got to download it. Let's see what happens.
Save link as. It should sometimes works.
No preview, download it. So it worked for me.
Okay, yeah, I'll try it again.
Not sure what.
Had a couple of notes.
Okay, fair
There's
enough.
other ways to access the file. I mean, I have it, so.
Yes. Anyway, so first point is, if you're going to play in the system dynamics sandbox at the graduate level, you really need to get John's book. It is a wonderfully written book. The formulations are outstanding. The writing is outstanding. And it's really the Bible of system dynamics. And, if you're just taking a one-off, I'm curious about what this is course, there's really no need. I think it costs like $200 or something. But if you're going to be a system dynamicist, you really need to acquire the book. So I just want to make a pitch for John there. It's a wonderful book. There's our lectures. All right. So I mentioned this the other day. I did add the paper by George Richardson, and they call him Nacho. His real name is Ignacio, I think is his real name. They call him Nacho. He was one of George's students. And they did a survey it ended up being 20 senior system dynamicists. And they asked them, what's your best practices? And so it's a summary of what is regarded as the best practices in the field by some senior people. So, that's in line with all this stuff here. And I did stick John Little's obituary here because I didn't really know where to stick it. Reference modes, again, just some of this stuff we've already covered, just refreshing your memory and putting it into the big picture. So we model problems from a systems perspective. We don't try and model the system. We don't try to create a digital twin. We try to simplify. Khaled wrote the paper on slicing a complex problem. Basically, he's saying if you've got a very complicated behavior mode, pick one of the modes that are intertwined and build that model first. He has some other stuff as well in there, but that's basically my main takeaway. That's how I think about it. And I showed you with some real data how you might do that. It's obviously from my training as a macro money guy, macro money economist, but pick your own area. But I gave an example of how to do that. And I put in a plug for my own paper on the optimal shape parameter. And I said I've tried to get the software people to introduce that forever. I think it's a worthwhile thing. We did do it for the Takeda project, if you remember that, Jim,
yep.
with Suleiman and Rafat, and they programmed it up in Python and stuff. And I thought it was valuable. it's not earth shattering, but it's valuable. We talked about how you would determine whether or not your model mimics the reference mode, the base run of your model. And if you have the numerical data, Sturman suggests tile stats. So we went through that. And there's some examples of how it's done for you. Here's how do you just stick it into a Stella model. How do you do that? There it is. We talked about a lot when you're specifying the reference mode, which is a picture of the problem, right? We also talked about that's a time to begin thinking about a scoring metric, particularly if you're making a game, but even if you're not. And the idea is, okay, if the reference mode is faithfully mimicked by your model, the model mimics the reference mode, the problem, to some degree of fidelity. And we can get into statistically speaking or qualitatively speaking or what have you. But let's say there's an agreement that, yeah, the reference mode is being mimicked by the model's base run. So the model's base run is providing an explanation for why the problem is happening. And now you have a vehicle for exploring policies or system redesigns aimed at improving the behavior of the reference mode, if you will, of the system. And we said, but really, complex systems rarely have a single variable obvious solution. The red curve is going up, it's bad. Every policy we try makes it go up a little bit faster, a little bit slower. Nothing makes it go down, except simulation experiment number 11. That made it go down. Ooh, that's the one, hooray. It's rarely that obvious. Usually we have a multi-attribute definition of what a good system behavior is. And we've said, what's a good city, right? What's a good marriage? What's a good, and it's all these attributes, right? And usually there's trade-offs, right? More of something leads to less of something else. The solution of one issue makes another one arise. So you really have to get a multi-attribute scoring mechanism and get people to specify their own weightings. And if they don't want to or can't, you can weight everything equally. And in principle, you could have a game, I suppose, up on a server and have many people from around the world really play the game and say, well, before you play, specify, there's 7 attributes here that make a good whatever. Let's say a clinical trial. Jim and I are working on that project. Well, what makes a good clinical trial? Well, we have these attributes. How do you weight them? Equally or no, this is more important than that one. Well, go ahead and specify your weights. Now play the game. And then later on, when the game is over, you can see how you did. And then how did your score from the multi-attribute function relate to the global score? When all of the weightings from people from the last 753 people who played the game and specified their weightings, how does it relate? And how does it relate to an equal weighting? I think that would be interesting. I don't think there's an optimal answer like 2 + 2 is 4. And everybody who gets 4 gets it right. And if you didn't get 4 for an answer, it's wrong. It's not as obvious. There's a lot of value judgment and subjectivity. So I think a multi-attribute scoring function allows us to begin thinking like that. And there are some techniques here for doing that, right? And I presented my example somewhere. Where is it in here? Somewhere I put that. Let's see. Is it in here? Title stats? No. I think I put it up here. Let's see. Discussion, David Anderson, Andy Ford, paper. Well, maybe I didn't upload that, did I? Seems like I uploaded everything. Oh, no, down here at the very last thing, McFadden, Cobb Douglas linear scoring metric. So I presented several different ways of preparing a scoring metric. There's no one right or wrong way of doing it. But here are some examples.
Do you try to get down to one scoring? I mean, even if it's a multi-attribute scoring metric, sometimes combining things to me logically may not make a lot of sense. Certain combinations make more sense than other combinations. So
That's
can,
such a
you can
generic statement. I don't have an answer for that. It's on the one hand, on the other hand, it's
what I
probably,
mean is I might petition, like when I certain things put together make sense, right? There's certain, but I might have to put together things in a couple of different groupings, and then those become the multi-attribute scoring.
there's nothing wrong with that. That's perfectly fine. Yeah, there's
Yeah.
no theorem that says this is the way to do it. I'm just offering
Yeah.
several different
Yeah.
ways of doing it. And like everything else in a PhD program, you got to justify. You can't just slop it down and then move on. It is obvious that move on. It's like, no, 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 no. Justify why you did. But if you can justify it, it's asked and answered. You know, if it's mathematically incorrect or something, that's a different matter. But it's under the assumption the math is, there's no mistakes, you know, asked and answered. But you got to be able to say, here's why I'm doing this, right?
Right.
Okay. So yeah, so I presented my, you know, here's the Stella model right down here. And you know, absent any other information, I would go with McFadden's Nobel Prize winning formulation, because you can always hang your hat on a Nobel Prize. They just gave it out, the Nobel in economics today. So two people from Sloan and one from the University of Chicago and MIT won the Nobel today. So that came out in economics, I mean, so that came out today. All right, so then we push on. So conceptualization, I would argue this is probably the most important aspect of system dynamics. It's maybe not the most glamorous because you're not writing equations or what have you, but you're thinking. Or others are thinking, others who know a lot are thinking, and you're trying to extract their thoughts accurately, right? So, so the first paper, just to remind people, is Jay's very short note on emphasizing that it's the process of modeling, the struggle to understand, to make your model mimic the reference mode, et cetera, that adds the value. That's where the learning takes place. It's not the model, like as a mathematical work of art that you would admire, right? And then Jorgen and Nat Mass make some good points here. It's an iterative process. It's not A to B to C to D, perfect model, but you always circle back as you learn more. Then I offered, if you remember, my sort of twist on this is employing Greg Hayden's social fabric matrix to help structure or organize the model conceptualization process. And I wrote some paper on this and what have you, went through Rod Gill's thing and what have you. I did goof around a little bit with some AI as well that I showed everybody that might be a way to go in, you know, use the social fabric matrix along with AI might be a way, and an expert opinion or whatever, to try and identify all the important stuff that should go into your model. Doctoral students should work on that. That would be great to see that as part of a doctoral dissertation proposal. We're going to use the social fabric matrix as part of the conceptualization process, and we're going to develop some AI prompts or whatever to arrive at a teachable, repeatable way of doing that. That's a paper right there that'll get published, guaranteed, probably in two places: a version for the System Dynamics Review and a version for the Journal of Economic Issues, I would imagine, where Hayden's paper first appeared. We mentioned the hexagon method and sector diagrams. These are standard things to help the conceptualization process. The sector diagrams are kind of in Stella, they're called modules. But they're basically the 5 areas from Greg Hayden's social fabric matrix are sectors, if you map them one-to-one, right? And then we talked a little bit about soft variables, because they're important and they should be thought about in the conceptualization process. You know, if you talk about morale is really important, let's say in the Air Force, I'll use an Ashley example, right? I think they sometimes have morale officers and things, but you say, well, I have no data set for morale and I'm going to run a regression. So you leave it out. There's no numbers on morale. Well, in system dynamics, we don't have to do that, right? There's a difference, as Barry Richmond talks about, between quantifying something and measuring something, right? And there's ways to add soft variables to our models. And I suggested a good thing for the doctoral students to do would be to take Barry's model where he had burnout in there and it wasn't quite completely defined, but there was a whole lot of clues, and see if you could reverse engineer his model and get something something close to what he did. That'd be a good exercise. All right, so then we talked about once we've conceptualized kind of what do we want, what are our important sectors, what do we want in the sectors, what are the soft and hard variables, what have you. We should ask, and then we identify stocks and flows and feedback loops and so forth to get the basic lay of the land, at least a first cut of it. How do we begin? And we talked about my hierarchy of the pattern modeling process, how that's what system dynamics is. System dynamics models are pattern models, but you don't arrive at the crime scene as a detective or seeing a patient for the first time as a physician with no knowledge, right? You come armed with real typologies and principles of economics, or in system dynamics, generic structures and principles of systems, right? So it guides the pattern modeling process, the system dynamics modeling process. And we had a little bit of a debate as to, do archetypes belong at the principles of systems level or at the generic structures level? Are they generic structures, or are they higher up in the food chain? We didn't arrive at an answer, just was kind of spitballing there. That would be a good little note for the system dynamics review if somebody could come up with an answer to that. But the issue also was when we talk about principles of systems in this field of system dynamics, that's kind of smeared together with principles of system dynamics modeling versus principles of systems, the characteristics of complex systems, and even the principles of the relationship between structure and behavior. So when you say principles of systems, that can mean different things to different people. So my point is there's a bunch of issues, definitional issues smeared together and unclear in that area, and clarification of that stuff. I don't think that's a whole paper per se. It might be a note, or it might be part of a dissertation paper where that's one of the many contributions made in the paper, clarifying that stuff. Then we went on to test inputs. We talked about them in 550 a lot, not really much here, but I've made some progress. I'm going to share. I have a molecule that I built for everybody, and you can take and use this molecule for the rest of your system dynamics career. I think it's kind of cool. We're going to circle back to this in a minute here. I just want to give the overview here of the new stuff. So there's a new molecule here, and I added Jack Comer's and John Moorcroft's paper we'll talk about when we circle back here. We talked about first order control, right? When we have outflows from stocks, one question that should arise if you're a PhD level system dynamicist is, are any of my stocks not supposed to go negative? And if the answer is yes, this stock, that stock aren't supposed to go negative, then you got to say, do I have first order control here in my formulations, my equations? The equations can be doing other stuff, but in addition to the other stuff, they got to be saying, hey, when the stock is empty, stop outflowing so the thing doesn't go negative, right? And I said, there's all different ways to do that depending on the situation. So I put them all together into one model here. I actually have another model from the first course I just got to add here. And then to make this complete, I just noticed that. So, because you can imagine there's a lot of stuff here. So sometimes I don't upload everything because I'm trying to keep track of stuff, the old stuff, the new stuff. So I got to add something over here. Yeah, Suzanne, go ahead.
So this has been a burning question I keep forgetting to ask you since we're talking about having stocks go negative and modeling soft variables. Is it possible to allow a stock to go negative as a means of demonstrating two soft variables, like maybe conflict and peace, where they would be on the other end of
my Romeo and Juliet model and exercise from the first course does exactly that, right?
Okay.
So hate is negative and love is positive in that model.
Okay.
So yeah, so it doesn't. There are times when it should go negative, but often you don't want it to go negative. A stock to go negative. So how do you make it not do that? And at the same time, do the other stuff the outflow is supposed to do and remain within the system dynamics paradigm. Because remember, we do continuous time modeling. We don't do bang, bang, on, off, up, down, black, white stuff typically. And I mentioned programmers, when they take an SD course and they build a model, every flow is if then else, is Boolean logic. And that's bang, bang, up, down, on, off, black, white stuff. And it might even work, but it's really not getting at what we're trying to do, which is approximating the continuous flow of things. So there are, again, we don't have to stare at a blank screen wondering, how do I start? Where do I begin? There are people over the years who have developed formulations that we can learn about and use. And these are summarized right here. And I got to add the first one. It's the one from the first course. I forgot to upload it. Some of the first order control formulations, not all of them, some of them involve a table function. And we discussed table functions in the first course. And I elaborated on the formulation of table functions here with a lecture that John did years ago when I took his course, his advanced course at MIT. And he showed how, unlike what Nordhaus said in his criticism of Forrester's World Dynamics book, that it's measurement without data and all the nasty things he said. The main thing, he didn't understand table functions, and he thought they were just these ad hoc things that you just randomly drew a line and said, oh, there, and John shows in this thing, and I give it to you here, along with the model. This is my handwritten notes, and here's the model that goes with it, that you can nail down often what a table function should look like through basic math and logic, and rule out big areas of the Cartesian plane and whatever, without the need to like run a regression to fit it to data or something like that. So that's a little more of an advanced topic, but that was presented. Of course, John in the book covers these things. His book is basically his courses, at least when I took them. So, all right. So then we talked about delays. So stocks create delays. We said there's two kinds: material delays and information delays. And then within those categories, there's first order, third order, nth order, and infinite order, right? And it depends on the circumstances as to which you want to use, right? One of the examples was in Jack Homer's paper. It's in the Stella model. But if we go back here, somewhere there's partial model. Here we go. Partial model testing. In this Jack Homer paper, he shows how when he tried to use a first order delay to fit the model to data, it didn't do a good job, but a third order did way better. Okay, so third order, not a first order, right? So, and then how do you find from some data where you're not fitting the model to data like a regression, but you're talking to people, how can you nail down the time constant or the order of the delay, right? And Margaret Hamilton, who did system dynamics and played the Wicked Witch of the West in The Wizard of Oz, it's different Margaret Hamilton, sorry, has a solution for that. That's system dynamics humor, simulation humor. Okay, then we pushed on and we started talking about expectations, and I didn't finish this presentation. That's where we kind of ended last time. So I'll go through this in more detail as well this evening. So let's leave it there. And that blends us right into proportional, integral, and derivative control, which also blends us all into ordering functions. Okay, so these things are kind of intertwined. And I was wrestling with what order do I show what with and what have you. So we'll just do our best to try and go through stuff in an orderly fashion. Takes us next to coflows. Remember, everything in a traditional system dynamics stock is assumed to be identical. So if it's money, like dollar bills, and you say, well, dollar bill is a dollar bill is a dollar bill, In fact, most money today is ones and zeros on a computer, right? The fact that they're identical doesn't matter. That's perfectly fine. The fact that order is not preserved. The order that a dollar bill comes into a stock is not preserved. So the dollar bill that came in first is not necessarily the dollar bill that leaves first when it's spent in that example, right? There's a mathematical mixing process that goes on, and items leave a stock according to a probability distribution. So as a result of, and by the way, if that's no good, we have other kinds of stocks in Stella, conveyors, ovens, queues to fix the problem. But one of the main well-known fixes for this issue is co-flows. So what we do, because everything is mixed together in a traditional stock, is look at the average attributes of the thing in the stock. So if the stock is people, we say, well, people are different. They're young, they're old, they're rich, they're poor, whatever. So you say, well, on average, what do we have here? So if it's educational attainment, and some people graduated high school, some have an associate's degree, some have a bachelor's degree, whatever, you'd have average years of educational attainment of the people in the stock, okay? Or average income level of the people in the stock and what have you. Now, if that's no good, there's other solutions, but a co-flow often gets you there. So we have some well-known structures here, okay? And then some more sophisticated structures. And one I helped, I kind of helped Ann do for her Moscow model. We'll show you there for morale of troops, okay, the average morale of troops. And I'll show you something I did for an aging chain for my Future of Ham radio model here. It's more sophisticated. And you're going to see this can get quite hairy quite quickly. So it can be tricky business. And then there's some other issues here that are helpful, including there is stuff on population modeling. How do you do that properly? And so there's a lot of Jims in the field of system dynamics. So Jim Thompson wrote a paper with Bob Eberlein that presented a way of modeling populations in a way that would satisfy a demographer, and it's not necessarily kind of the standard system dynamics chain from young to middle-aged to old and what have you. Okay, and Tom Fitteman weighed in and whatever. So there's some useful kinds of structures here that are in this area. They riff right off of these structures I'm going to show everybody. Okay, somebody was saying something maybe, or
no, I was forecast. I can wait till we're gonna do forecasting tonight.
Yeah, that's up here with expectations. Expecting the future is another way of saying forecasting the future.
Yeah, okay. That's always like yeah, I'll wait till the forecasting section to ask my question.
So then I'm getting to the point where this is as far as I got with redoing everything. But just to sort of give the sweeping overview, we're almost done with the general presentation of where this is all headed. The next big issue is resource allocation and attractiveness. So you have a limited resource, time, money, personnel, and different competing demands for that resource. How do you allocate things? Okay, and that kind of smears in with attractiveness. Well, what's the more attractive use of the money or the whatever? Learning curves is big. Okay, so how do you represent learning by doing? At least in economics, that's a big deal. The more widgets you make, the better you get at making the widgets, the more efficient you become. And if you pass that efficiency along in terms of its lower costs, unit costs, then you can capture market share with lower price, for example. So, Moore's law and all that kind of thing. So how do you do that? And we got some interesting models here. And one I did with John some years ago, we'll take a look at. There's a nice new Stella version of it. Over here, we'll get into discrete formulations. Well, we do continuous time modeling, but how come Stella and Vensim or whatever allow discrete formulations like infinite order delays? Well, if you read what Jay has to say about it, Jay doesn't object to discrete formulations. He has, we quote it in Suleiman in my paper with Alex Smith, that Jay says basically a first cut should be continuous, but discrete formulations at some point are perfectly fine. So when is it appropriate to use discrete formulations? And in particular, we're working on a research level with behavioral economics. How do you bring insights from psychology and behavioral economics into our system dynamics models to enrich them, to represent what humans really do when they make their decisions? Well, the behavioral economists and psychologists, more the behavioral economists, because they build more models than the psychologists do, use discrete time. So how do you represent what they're doing? How do you replicate what they're doing so they're convinced, yeah, you got that right, you replicated the stuff from my paper? Then how do you put that into our otherwise continuous models? Or is it possible to translate them then into a continuous representation and stick it into our continuous models? So that was the basis of Suleiman's dissertation. We got some results here. It's very interesting. Parameter estimation, we'll get into that because doctoral students need to do that. Then we'll start building a model step by step. And whether it's the filtered water model or another one, I haven't decided yet. We'll see. We'll talk a little bit about synthetic data experiments. What are they and how do you use them? It's pretty cool. Policy optimization and Monte Carlo experiments. We'll learn how to do those. Building confidence in system dynamics models. So very important if you want somebody to believe your model and use it. How do you do that? And we're going to add some stuff in here that I think is very important in economics to get economists to believe or say, okay, I see what they're doing. It's not the tool I would use, but I get it. It makes sense and whatever. So it's not in here yet. And then how do you document a model and make sure, because that's if you're going to be writing up models in papers that go to a journal for your dissertation, you have to know how to document these things properly. And we might talk a little bit about games if we have time. All right. So that's a sweeping overview. I've got a lot of it updated, new models in Stella. I've tweaked them. I've said, oh, that doesn't make sense, or that might have been incorrect, or that's a little goofy. Let me fix that. You got so many models, thousands of models. I'm not even sure I'm always got the latest version of something. I try to keep an orderly, C drive and all that, but, lots of luck sometimes. But all right. So let's start by looking at test inputs. Very important area, right? So let me just get out of here for just a moment. So remember, big system dynamics models are built by thoroughly testing little system dynamics models, generic structures, archetypes, molecules, assemblies, whatever we're going to call them, and then hooking them together. And then testing those, and then testing a new piece, and then hooking all that together and testing it again. Test, 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 test. Okay? Because otherwise, if you just, this is very common, you'll get somebody who says, oh my gosh, system dynamics is the tool I've always imagined but never knew about. I will solve the world's problems with system dynamics. And as fast as their hand can move the mouse, they are plopping in stocks and flows and feedback loops and connecting arrows and whatever. It's proc brain dump. That comes from SAS. When we were graduate students, we used SAS. SAS has procedures, proc regression, proc this, we always said, proc FU, proc lunch, proc whatever. Anyway, it's proc brain dump, right? And then what happens is you've got 75 things all connected together in some crazy bird's nest. And then you hit the go button for the first time and it does something crazy or it doesn't run or whatever. And then you're like, I don't know. And they bring it to me. Can you help me? Sure. And I open them up and it's like, what's going on? It's all crazy. So I always say, don't throw it away. Good brainstorming has happened here. But let's just pick one thing, pull it out of there, and let's start afresh. Is there a molecule that represents whatever you're trying to represent here? and we go from there, right? So in light of that, that's a big picture. How do we test to see if our piece of structure is okay before I attach it to another piece of structure to make a bigger mousetrap? That's the key. And we use the signature way. There's other ways, but the biggie, overwhelmingly, is test inputs, right? So I've made a molecule for you that you can use that has all of them in there. And all you have to do is specify 0, 1, 2, 3, 4, 5, 6. There's 7 different possibilities, and it'll do it for you. Okay, so let's take a look at that. You're welcome.
Thanks, Mike.
Yeah, there we go. Like Sturman always says, use it all you want, just give me attribution when you use it. All right, so here's the molecule, okay? And you see we have here, if you specify 0, you have equilibrium, and it's over here in blue. I should have probably made this, I should just do that right now. Make that blue as well. Did I do that? I guess so. I thought oh yeah, it is blue already. Okay. Sometimes it's a little hard to see the colors. So, blue writing with the text tool here, blue icon, and then over here, you just stick in a 0, a 1, a 2, a 3, a 4, a 5, or a 6, depending on which of these you want. So 0's in here, and we run it, and you get equilibrium, okay? If you put in a 1, everybody can see this, I hope, on their screen? Can you see the panel on the side here? Yeah, okay. So if you put in a 1, you get a step. If you put in a 2, get a pulse. You put in a 3, you get a sinusoid. If you put in a 4, you get noise. If you put in a 5, you get a ramp, which is easier to see than 6, which is exponential growth, but you get that as well. Okay. So all of these are possible. Okay. And one thing just I wanted to show you here, which was a little tricky. Actually, this probably should be down here. I think I changed that earlier. Make it a little cleaner. I like my stuff to be clean. Some people don't care. I'm a little persnickety.
Okay, I just want to say that's very impressive. I'm really liking this a lot.
Okay, good. That's the right answer. Notice what I did here with the noise. Now, I use a uniform distribution. You can use other statistical distributions here. There's all sorts of, you'd want to use a Poisson if you were representing irregular arrivals, like if you were modeling Home Depot or Walmart's checkout kiosks, and people are arriving irregularly, or at the Boston Marathon, a water station or an aid station, and the runners are coming irregularly. That would be a Poisson distribution, not a uniform distribution. Uniform, every number between the min and the max, minus 200 and 200, is equally likely. And then NaN means there's other. So if you hover over here, you see it'll give you the definition. It used to be you'd right click. In this version now, if you right click, you'll go to the Stella website. So now you just have to hover over it. And you see it was the minimum, the maximum, and then the seed. So a seed means you can put in any seed value you want. 1, 2, 3 is fine, let's say. And then it will always give you the same sequence of random variants. But if you want to have different random numbers every time, then you say NaN, or that's, I don't know what it exactly means. It means no value, I guess. So that would
not
be
not a number.
not a number. Okay, good. So see, I have that in here, so it gives me a different sequence every time. But if you want the same sequence so you can repeat an experiment, you would put in some seed value here. Then if you look here, the other spaces are taken up with, just leave them alone. But I did put in how often do you sample? Because if you don't specify anything, I put in 0.5 here, it'll give you a random variate for every DT. So if DT is very small, it's going to give you a lot of them. And I said, no, every 0.5 of whatever this thing is in, did I say here what time? Month. I should have just said time here. Time. It'll give you much fewer, so it's not as cluttered here. Okay. All right. Anyway, so that molecule is downloadable for you, and it's I think it's just very handy. You can copy and paste it into your model and use it as you will.
I think the only thing I would do additionally is I might want to control some of the parameters around when, you can do it by, you have them in there, but I'd maybe put an interface with some controls over the test inputs.
A good job for a PhD student.
Yeah, that's because that building test interfaces are really important.
Okay, so where am I? Okay, so there's a couple papers here by Jack and John about partial model testing using test inputs and whatever, and how important they are. And I just wanted to call your attention to John's. They both appeared in 1983 at the SD conference, which was the first, wasn't the first SD conference. It was the first official SD conference. And I was there, I was a student. And I met all these guys, how many years ago already? 41 years ago or whatever. Here, in fact, he even did it earlier than that. But at any rate, what's interesting in here is he talks about the Carnegie School. And I remember John talking about that. So here at Carnegie Mellon University, Carnegie School, and it was Herbert Simon was there, Nobel Prize in economics. Richard Sayert was a famous economist, but he went on to be the president of Carnegie Mellon. He would write a lot with March and Williamson. Oliver Williamson was the father of the new institutional economics, very famous. So this is all the Carnegie School, the big names, and their thing was, their underlying the work of the school is the powerful notion that there are severe limitations on the information processing and computing abilities of human decision makers. Okay, so it objects to traditional economics of modeling human behavior as like Mr. Spock making optimal decisions, solving constrained optimization problems in their head and whatever. And John Moorcroft is arguing that when you do system dynamics modeling, you're representing bounded rationality. Okay, and the way he makes like the theoretical argument, then he shows an example and he takes Forrester's market growth model. Is everybody famous with that model? Famous. Everybody familiar, with that model? Forrester's market growth model.
Yeah.
I replicated it in Stella. I should upload that. I got to start writing notes here. I got to upload. Forrester's market growth model. And I said the first order control model I got to upload. So I'm writing notes to myself, so I remember to do that. At any rate, this is a very, very famous Jay Forrester model where he showed how endogenous cycles are possible in a company and how a company can limit its own growth. Okay, so it's a very famous model. And what John shows is that the sectors of Jay's model follow in isolation with test inputs are bounded rational. They're rational, bounded rational. You don't have complete information, but they're perfectly rational in and of themselves. But when you hook them all together, you get the irrational behavior of the company, oscillations and self-limiting growth. So it's consistent with the work of Simon and Sayert and March and Williamson and all that stuff in the Carnegie School. So we're doing the test input stuff in order to make sure our hunks of structure don't do anything stupid when we hook them together, but it's also in harmony with other things, right? So you can make the argument in your paper you're submitting to a journal that, you know, you've tested each of your model sectors or subsectors for bounded rationality, Site-Simon or whatever. And again, you're bringing the receipts, as they would say, to your article. You're not just freestyling where somebody's going to, where are you getting this stuff from? You have legitimate, reasons for doing it. Okay. So far, so good. Okay. So then we went on to first order control. I just wanted to show you that I've put them all, I've redone them and put them all now in one file, including some other ways of doing table functions. And there's different, more sophisticated ones where you have order of preference and so forth. We did cover these already, but just to give you your bearings, over here, if you don't want to do a table function because table functions are not possible, let's say you're doing this in R, Python, Simulink, Minsky, they don't have the table function capability, what do? Well, you could use an analytical function like this right here, code that in, or what I did is I specified the ordered pairs here in Excel or Google, I think it's Google Sheets, right? And then I fit a polynomial to it. It's a little small here, but you can see there's the equation right here. And you can put that equation in your model. So either this equation or this equation in your model. This one's sort of a theoretical equation. This one I derived from ordered pairs. In either case, I didn't derive it from inside of Stella, right? If you're using a software package that doesn't have that capability, or for some reason a referee at a journal says, "Why? I don't trust these things. I want to see an analytical function." You'll hear stuff like that. So for example, when would you hear that, or why would you want to do that? Well, certainly in economics and in management science, where Sturman plays, what he teaches his doctoral students to do is to camouflage what they're doing. So he would always argue to us, well, system dynamics has a bad reputation among many academics, which is silly because it's calculus. So then if somebody says, I hate system dynamics, they're saying I hate calculus, or system dynamics isn't useful, calculus isn't useful. He said what they really were saying, I didn't like Forrester's world dynamics model, therefore I don't like system dynamics. So that's silly. It's like, I don't like this model that was done with calculus, therefore I don't like calculus. Stupid, right? But he says, what are you going to do? These are the people running the journals. They're the referees. You got to deal with these people. So what do? So John would have his students learn how to build their model and translate it into the traditional ordinary differential equation view of it, like going from Fahrenheit to Celsius, or integral equations, either way. And he said, if you want, use Greek letters. They like that. But what do you do with a table function, right? It's still, that's clearly a computerish thing, computer science-ish thing, interpolated ordered pairs. Well, you can put in the analytical function, right? And then you don't say system dynamics, you just say I simulated, the model's nonlinear, so I had to simulate the results. I use a numerical recipe to simulate the solution. You're doing system dynamics, but the referees don't know it. Okay, so there's a lot of reasons you might need that in your hip pocket as you're going forward, as trying to publish papers in journals, right? And getting around the refereeing process. Okay. So we had already looked at table functions, but I just wanted to show you that. Okay. All right. So then we did talk about the delays, and I think we're good there. I think I have everything in one. I can't remember, did I, when we did that, did I have everything in one file? I can't recall. Or did I have different files?
For what?
One
For
file?
what?
For delays. information delays, material delays, and all that.
I don't. When did you do? Did you do it already this week? I remember you having one file before where you could put in different delays. There was one file.
For both information and material.
Now I don't remember.
Okay, so
You had the infinite delay. You had a. I think it was all in one file. But
all right, let me see if you guys know this or not. I mean, it doesn't matter if you just refreshing your memory here, that's fine. So this is the file. It has everything in one place now.
Okay.
So why are there two different kinds? That this thing will change if you change the time constant here. Okay. So if you try to delay information, change the time constant, you get a different equilibrium. It's not the case if you use the right type of formulation. And then we have the material delays, right? And the equivalent information delays all in one file. So I'm not sure. You remember that? I went over all that. I just don't remember when I did it, if they were all in one place. If they weren't, now they are. So you don't have three different files. They're all in one place. Okay, that's over here. Comparison among delay structures. Okay. And then expectations. And that we covered mostly last time, but I've done a bunch of things here. So I want to update everybody on the whole expectations thing. Because I think this is kind of important. So the first one is sort of the generic system dynamics formulation for expectations that is consistent with Kahneman and Tversky's anchoring and adjustment, if you remember all that. And I did put in the molecule for test inputs now, right? I guess we have equilibrium there, but if we go to what is a ramp is 5, I guess. This should fix. Yeah, this time scale you can't see, but it fixes it. You don't get the railroad tracks, permanent railroad tracks. Okay, so that's the generic structure for a mathematically correct expectation structure consistent with a basic Kahneman and Tversky anchoring and adjustment formulation from psychology. Okay, so what else do we have here? Well, just to refresh your memory, if we go to my paper, this was the one in the feedback economics book. This is where I used that formulation to fix the Herod model. Remember, I did the Glenn Grimes thing. Just want to refresh your memory. So I tested it with real human expectations data. I estimated the parameters. Here's Herod's model. I severed this link right here, right? He has the golden age and all that. And then I added that expectation structure. I had to tweak it a little bit, but it's the basic structure. Now I have it a golden age again. And then the question is, are managerial expectations mistakes in expecting the future responsible for the trend in the cycle, as Herod said? Yes, blah, blah, blah. So that's an application of this structure here. Okay. But guess what? There's a simpler version of it over here. Okay, so this doesn't have as many stocks and things happening right at the same time. It's a simpler version. Okay, so we still have a perception. This is the same. That's the same. Okay, but the trend, if we go in here, oh, look at this. Wait a minute. We have the trend function. So if you go into Stella here, there's a trend function. Okay. So instead of all of the gymnastics that you would have to do what I did, you can use a canned function. And a lot of veteran system dynamicists do that rather than building everything out. You know, it just takes a lot longer, right? Okay. So again, this molecule is up there for you so you can play around with it and take a look. I believe Jim Linus, I'm going from memory here because it was quite some time ago when last I looked at it, but Jim Linus has a book that Jim Hockenda loves. Remember, there's a lot of Jims in system dynamics. Jim Thompson, Jim Hockenda, Jim Hines, Jim Linus. That's 4 biggies. There's probably other ones. Jim Duggan. It's another one, right? A lot of Jims. So you can take a look at this.
Yeah, you can buy this book used. I recommend it.
What is it? Corporate planning and policy
Policy design. By Jim Linus, yeah.
Very nicely, it's amazingly structured. It's a great book.
And I think he does this. I haven't looked at that in a while, but I believe he does this simpler version in his model that he builds up. By the way, the model in that book is a generic model, but it's really Harley Davidson, in case you didn't know that.
Over there on the floor.
So if you get his book, Jim Linus's book, it's Harley
Yeah,
Davidson.
I bought it. You can't. It's not in print anymore. You can just buy it used. It's in Dynamo too, so that's the other. You're gonna have to learn to convert Dynamo, which I think you had in your class, right?
551, Colin makes you do that, yeah. Okay, so, all right, so there's the more elaborate version. There's a simplified version, right? And then let me show you some applications. I do this in the first course, but it's worth revisiting. So in the first course, I build an arms race model. You guys remember this one? Arms race model, where we take the basic molecules and say, we tested these in isolation. Now let's hook them together and make something. All right, does everybody remember that? From 550? One of these things, as though it never happened.
No.
All right, at any rate, so this is the arms race model that we did. So notice we have, here's a molecule right there. There's a molecule right there. There's a molecule right there. There's a molecule right there. One right there. One right there. There's molecules all over the place. They're all first order, but when we connect them together, we have a major fourth order system, right? And we talked about the goal for this stock and the goal for this stock can be tweaked because of fear. So you say, well, country B wants whatever they think country A has, plus a margin of safety just to be, because you don't know, you're using spies and satellites and listening devices and what have you to figure out what the other guys have, but we could be wrong. We better pad our estimate just to be safe. So if you add a little padding here, remember, we got an arms race just because people are scared or whatever, but we really got railroad tracks here. We have steady state error, right? So remember a PID controller or a proportional control structure, which is this one here, and this one here, and this one here, and this one here. Those proportional control stock, target minus stock over tau, almost always introduces steady state error or is quite susceptible to steady state error, right? So it's not surprising we have steady state error. Both sides are trying to catch one another, and neither side recognizes that the other one is growing at a particular rate. So at some point, not necessarily right away, but at some point, if every year they're growing at 2%, what are you going to predict for next year? 2% more, right? That would be completely rational. And the model can't do that. So what's the fix? Well, the fix is the same thing as before. We add in that expectation structure. So we're adding in this guy. Okay, is that the one I showed you, or did I show you? I'm trying to remember what I showed you in general. That's the one I showed you. I added in that one. Oh, I failed to. There's also, so here it is again. that one I did, the simpler one I just showed you, and this one's also in the arms race model, but there's also, look at this, I forgot to show you this. Let's see, here. So another canned function is forecast in Stella. So if you don't want to do all of this, so let's give it a 6. Exponential growth. Let's see how we're doing here. I'm not sure I ran, what have we got here? 10. I don't know if it's catching up here or not. Let's see. 28. So the two forecasting techniques are the same. Oh, but I remember what I had to do. So depends on the situation, but sometimes see forecast horizon here. In this case, it was 6. What if we make that 0? Sorry. What happens now? How are we doing now? Yeah, so we got, it's a little hard to see on the scale, but we got pretty close, and it's, DT is not infinitesimally small. So if you're not projecting way ahead, you can get the two to match using the simpler case. And over here, same model now. You can see now it figures out they're following each other. They're identifying the growth trend in each one, and they converge rather than having the railroad tracks. So adding in the expectation or forecast molecule can be quite important at cleaning up steady state error. Okay. Now I know you're like, wow, there's a lot of stuff here. Yes. And your job is to, not now, but when I'm not around, take a look at this stuff and see, oh, he took this and plopped it in here. He's connecting molecules together to make other things or to fix problems or whatever, right? Another thing you should be saying as a doctoral student in system dynamics, I have an outflow here. Do I have first order control? Yes. If that goes 0, the whole thing is 0. Good. Ta-da, right? So these are the kinds of things you want to be, and you want to be noticing, oh, I know that molecule. I'm familiar with that one. I know that molecule. I'm familiar with that one, right? These are the skills you want to be building up. Okay. What else do we got here?
I have a question, Mike.
Yeah.
You referenced a paper by Kahneman and somebody else for
Tversky.
modeling.
Amos,
Huh?
Kahneman and Tversky.
Is it in here?
No.
What, do you know the name of the article?
The original, they're probably their most famous paper where they discuss all this stuff is in the journal Science. If you say Kahneman and Tversky Science, like it's like 1979 or something, it's probably referenced in there. It's very famous, but I don't have it right off the top of my head.
Okay.
Because they did so many different things. Anchoring and adjustment is not the only thing that they did. They're big with prospect theory. That's probably what they're most famous for. Asymmetric preferences. People attach more value to not losing $100 than they do to making $100. Okay.
Okay, I'll find it. I was yelling at my dog. Sorry.
Yep. All right. So let's summarize. We have the basic generic expectation formation structure, and it's cleans up steady state error. It's consistent with Kahneman and Tversky's anchoring and adjustment. I used it to fix the Herod problem, right? And there's a simpler version of it. And here's an example of using it to fix a problem, a steady state error problem with an arms race model, right? But also they're expecting, forecasting what the other guys have, right? And I mentioned that I believe that this is in one of, in Linus's book. It's like in an appendix. I'm going from memory here, but as well. So again, you know, it's bringing the receipts. Radzicki didn't invent all this stuff. I invented some of this stuff, but not all of it. Okay, now Sturman says, well, we can go this is the generic, this is the simpler version. He has a well-known paper where he goes beyond this, and you can read it if you want. And he has a whole chapter in his book about this, formulating these structures. But he gets into versions of this, of the generic structure, the sophisticated one, including like a sea anchor and all sorts of stuff. So if we go, we're not going to go through the whole paper here. It's a lot, there's a lot going on here. But if you look at some of his, so that's the basic, you've seen this already. That's the Kahneman and Tversky thing, right? And he's using it to forecast inflation. This is called the Livingston data. Mr. Livingston, I presume, right? In Africa. No, that's a different Mr. Livingston. Livingston was a columnist, an economics columnist for the Philadelphia Inquirer, I believe. And he would assemble this expected inflation data set. It's very famous. So somehow John got a hold of it, and he's trying to replicate the expectations in the Livingston data set. And he's had to go beyond the basic generic Kahneman and Tversky structure. So he has a sea anchor model that does better. Okay. So, you can go beyond, you see, he's got the different tweaks and twists and extensions of the basic model. So don't just say, well, here's the generic structure. Here's a simpler version. I'll use either one and I'm done, right? You sometimes have to modify them for the situation you're in, add to them, subtract from them, whatever. And John gives you an example of taking a basic structure and manipulating it, adding to it to fit the situation that he was in. And he didn't just ad hoc do it. He was thinking about, well, what would people do when they're forming their expectations? You can read about it in the paper. Okay, now you'll see if you go through a lot of these materials, I've mentioned this before, I'll mention it again now. I'm just looking for my clock. Okay, we got time. That I have put excerpts from discussion boards where somebody posed a question, a new person, a newbie, how do I make my system dynamics model do this? Or how do you represent this? And all the luminaries weigh in. And it's funny, they don't agree. Or I'll say, well, I agree with my good friend Jim Hines that, but, and then they give a different formulation. Like everybody, including Forrester, is weighing in. Forrester, Sturman, Hines, Andy Ford, Jeff Coyle, Bob Eberlein, George Richardson. I mean, how many is that already? 7 or 8? And there's more. So it's really fascinating to see them debate one another about the proper way to represent something, right? And if I were to summarize, and it was for all different kinds of formulations, if I were to summarize, like, big picture, what went on with these debates amongst these luminaries, I would say it's one question is, do I need something very simple here? Because all the main issues are over here. So there's no need for me to build a giant mousetrap here. It's not, the issue isn't there. And a simple formulation is just fine. And I'm going to worry about over here in my model. That's one kind of issue. Then the other issue that seemed to always raise its head was, are we talking about a mathematical thing or what a human being does? So a lot of these sort of engineering types would come in with, well, my mathematical representation handles all possible, situations that can be gotten into, therefore it's superior to all of yours. And then Sturman would say, well, but that's not what a human does. A human being is imperfect. we're trying to capture what a human being would actually do, this bounded rationality and whatever. So they're both right. The big time math thing is best because it mathematically handles everything. But a lot of times that's not what people do. People do this. And if we're trying to capture, like, why are we having a problem here? You got to model what people are really doing. So these excerpts I have from these discussions at various places, and they're fascinating to read if you like system dynamics, to see what all these giants in the field are thinking about and how they're bickering with one another and what have you. Okay, so why am I telling you that other than just to tell you? Well, we have a couple other things here. So Clark and Umholtz, and I replicated their work over here. There's a model here. Let's see if I have it. Yes, I do. So some years ago, these guys came up with this paper in the SD Review. I'm trying to remember what year this was. 1989. And they say this note discusses incorporating foresightedness into a system dynamics model. This means projecting future values of a variable and using the projections to affect model results. For example, in a marketing problem, assume that the need for additional production capacity depends on management's perception of delivery delays. An increase in observed delivery delay triggers plant expansion and vice versa. If it takes a year to change plant capacity, then it would be useful to project the value of delivery delay a year or so ahead, right? Makes complete sense. Now they go all mathy on you. The Taylor series expansion is discussed as a foundation for projecting such future values of a variable. So I remember as an undergraduate sitting in Dr. Painkratz's second, I think, calculus course, learning Taylor series expansions and other series, power series or whatever, and thinking, when in my life will I ever use this shit? I cannot imagine when I would ever use it. And then voila, I'm using it. Okay, so a Taylor series is taught in all the calculus classes. In this proposed approach, the Taylor series is approximated in Dynamo. So to predict the value of a variable an arbitrary time period into the future based on the variable's current and past values. Comparing current and past values provides slope, position, slope, rate of change of slope, and so forth. So position, velocity, acceleration, acceleration of acceleration, acceleration of acceleration of acceleration, and so forth, depending on how many terms of the Taylor series expansion that you want to use. Okay. Again, Forrester's classic market cap model, the one I said I have to upload, his market growth model is used. So a lot of people, you'll see this, Peter Senge uses it to see if econometric techniques are can be used to estimate the parameters of a system dynamics model accurately. It's a well-known model of modest size, so lots of people use it to test things in system dynamics. So again, so John Moorcroft used it to show bounded rationality. These guys are using it to show off their Taylor series expansion technique here for forecasting. Okay. So they're going to alter it to demonstrate their method. The delivery delay recognized variable in Forrester's model is replaced with a variable that projects delivery delay 8 months into the future. Okay, and you're not surprising, it's going to do a better job. It's going to damp the cycles and what have you. Okay. I see your hand, just a minute. So it gets a little mathy here, but this is the Taylor series expansion. Okay, and they're basically, they say in a footnote, just look at any calculus book if you want the details. And they give an example using that magic number E. Okay, but now they start telling you how to do it in system dynamics. And there it is. And then they apply it. They're showing you how this is Forrester's original model. And now they're going to modify his model. As you can see, they're damping his oscillations. The dotted line is with their modification in the model. I see the hand. I'll get there in 1 minute. So what I did was I reproduced what they said to do, and I put in the test inputs over here. And again, I don't know what's loaded in here originally now. What we got here is, 0 should be equilibrium to begin with. There's equilibrium. And of course, if we want to have, I don't know, exponential, you can see it caught right up. Initially after the shock, it got behind, but then it caught right up and started expecting it. So it gets rid of the steady state error and does a very nice job. One last thing, and then I'll answer the question. In here somewhere, they get into sort of the Sturman versus David Peterson debate. Let's see here. I want to get the exact quote, otherwise I'll just tell you. Let's see. Basically, they're saying it's a mathy thing, but it's not necessarily what humans will do. I guess that's what I'm trying to, they quoted, and I just can't find the quote real quick here. So that goes back to what Sturman would say versus, other people about, is it a mathy thing or is it what people really do? Okay, Nasia, go ahead.
I thought Jay Forrester said that system dynamics should not be used to like make better predictions, but to just model how people like naturally think to improve their decision making. Would you say that this application is something outside of that, or something that, I mean, I can see obviously how this would be useful to a manager to improve their system, but does this kind of counteract Jay Forrester's suggestions on the purpose of system dynamics?
So you'll see in the next thing I'm going to show you, we'll answer that question. Actually, it'll be Professor Saeed will answer that question in his paper. But I would say, channeling Jay, but having had a million conversations with him over the years, he would say, trying to build a system dynamics model to predict the future is a fool's errand, because you can't, not with any certainty, not on any time frame that's useful. You can predict 1 nanosecond what something will be like. I predict it'll be like now, 1 nanosecond from now. Oh, I'm right. But that's not useful, right? So he said, trying to build a model for that purpose is no good. But he said, on the other hand, people do forecast. And it's how is the forecast used? That's part of the structure of the system. And if they're going to forecast, what's a good way to do it? But it should be for the purpose of making the system behave better, not to try and predict the future. So I think that's what he would say. But Kala does answer that very shortly here. But it's a good question. Okay. So, all right. So again, we have a mathy thing and we have a Sturman behavioral human thing here. Okay, and they both can be used. Barry Richmond, there's a D memo where he long ago in 1977 was trying to figure this out, and this is kind of like these other things here. So I just put that in here to give Barry credit for being one of the first people to think about this. Okay, so Najla, let me have Professor Saeed answer your question. Okay, so college paper, can trend forecasting improve stability in supply chains? A response to Forrester's challenge in Appendix L of Industrial Dynamics. So that was 2009. That wasn't that long ago. So let's see what my good friend Colin has to say about all this stuff. The use of trend forecasting in policy design has been viewed with reservation in the system dynamics community. Ah, that's what you were saying. Jay Forrester pointed to the amplification of changing conditions created by the use of trend forecasting in policy as far back as 1961 in Appendix L of Industrial Dynamics. So in that appendix, Jay said, look, if you forecast by trend forecasting, you can amplify instability. The self-fulfilling nature of forecast was explored by Linus in that book we were just talking about. And he reported the destabilizing impact of the use of forecasts and decision-making in further detail. Barry Richmond supplemented this work by that trend macro that I have. I have the D memo in there, okay? Confirmed what Forrester and Linus were talking about, and so forth. So Khaled is acknowledging kind of what you're alluding to, Nejla. So Khaled goes on, trend forecasts apply to the determination of ordering policies and supply chain management systems often seem to exacerbate periods of shortage and oversupply, sometimes referred to as the bullwhip effect. Also no good. So it is not surprising that trend forecasting has been largely viewed in the system dynamics community as a source of instability and as a dysfunctional basis for policy. Trend information has been used, on the other hand, with great reliability in engineering in controller control. The analog PID control process can be expressed in the following simplified form. So Khaled is saying, now, wait a minute. Before I came an SD guy, I was an electrical engineer and I studied PID controllers. And we use trend forecasting all the time to stabilize systems. So what the heck? Okay. So he goes on, and I'll show you his model in a minute here. He presents a system dynamics representation of PID forecasting. So it's more engineering-ish than...
Wasn't Jay Forrester also an engineer?
Yes.
Or did electrical engineer?
Yes.
Yeah. Okay, so he would have also known about this, presumably.
Yes, he has patents based on PID controllers when he worked in Gordon Brown's servo mechanism laboratory. So, so in and of itself, it might be okay, but used in a broader system may or may not, or maybe it's how it's used rather than whether it's used.
I would think that if you're driving like some forcing functions, and it depends on where you put it in. If you put it in as a control, forecasting might be good. That's what Khaled says, right? He did a lot on PID controllers. But if you're putting it in to establish like a position in a table function or something like that, an index into a table function, you could destabilize the model.
All right. So let me pull up, before we go to Khaled's model, I have it in the Phillips model. PID control theory principles. We've kind of discussed this already, but let's go through. So that third molecule we did in the first course, a first order negative feedback loops structure with an explicit goal, target minus stock over tau. That's the P in PID control. That's proportional control. Proportional control alone leaves a steady state error that can be reduced, but not eliminated, by increasing the proportional control gain, by changing the parameters. Okay? So by speeding up the error correction process. Okay? So, but you can't eliminate it. And that's what we've seen, steady state error in some of these things, right? Desired inventory minus inventory over tau, right? Plus average sales can lead to, without average sales can lead to steady state error, for example. So what do you do? This is classical control theory. It's not modern control theory. Like one is analog, one is digital. I'm not an electrical engineer, but how about the I? Integral control eliminates the steady state error. So there's a way to get rid of it, but is very destabilizing, creating the likelihood of oscillations. The greater the integral control gain, the stronger you make it, the greater the instability. But then we get the D. Derivative control acts to dampen the oscillatory tendencies of integral control, but draws out or delays the system response. So there's no free lunch here. There's trade-offs. The greater the derivative control gain, the greater the damping tendency and the response time. Okay? So if we go back to Collins's model from Collins's paper, this is what he's doing. He has an inventory control system, right? So what's derivative control here? First of all, he gives it a weight. And it's correction from trend in inventory gap. This is his point. Well, what do you mean you can't use trend or trend forecasting to stabilize a system? Okay, so what's the trend? Okay, well, here's the gap. So there's a gap between what you want and what you got in inventory, and you get the average gap. So that's that the third molecule we use. It's also the proportional control molecule, right? And then what we have here is the inventory gap minus the average inventory gap over the time to change the gap, to close the gap between the newest gap and the average gap. Okay. And then you give that a weight. That's derivative control. That's the trend. Okay. The proportional control is you take the gap, the difference between what you want and what you got, and you divide it by tau, target minus stock over tau, and then you give it a weight. So there's the weight to the proportional control. And that's standard stuff. And then here's the correction for the gap. And what you're going to do is over the time constant, accumulate it. That's the integral control. And you give a weight to that. And then in this case, the production, the overall control is the sum of proportional, integral, and derivative control. You can see here in response to a shock, it dampens things quite nicely. So Collett is saying properly used in a PID system, you know, it's okay, I guess. Now, the other thing I have here is some stuff by Bill Phillips. Now, we all remember Bill Phillips, right? We looked at the Phillips machine last time, right? The movie video, right? He was the electric.
Before you go on, so in Collins's his assessment of the information is used for the control, or how the quality of the information is used for the forecasting. I mean, that's always a challenge in businesses, because a lot of times the information is problematic. You know, it's the accuracy of the information.
To be biased.
Yeah, it's biased, it's uncertainty.
Delayed.
Yeah.
Yeah. So his paper was just making that point. It wasn't with a very simple model. It wasn't representing, you know, a real organization that has all these reporting delays and managerial biases and
because those have like
measurement errors and whatever. So yeah, so I mean, yeah, you make a good point. So if you were really doing this, you would be first trying to model if they're even doing this, what's going on, and then secondly, if they are, is there, you know, you need to speed up the measurement of something or be more accurate or whatever. No argument. Okay. All right, so remember Bill Phillips. We looked at his video of the Phillips machine, the water flowing around in tanks and pipes, stocks and flows, and the floaty was graphing the stuff and whatever. It was an analog computer of a macroeconomic system right after World War II. He made it out of a Lancaster bomber parts and whatever. And it was genius thing. And then of course, digital computers came along and that was that, but still it was quite the achievement. Well, Phillips continued on with sort of applying electrical engineering stuff to economics. Okay. And so if we look here, oh, by the way, before we do that, I'm remiss. I need to show George's thing because Hal had mentioned George. So here's this is from George Richardson's lectures at SUNY Albany. And he gives you some examples of PID controllers here. So he's telling you what to do. Anyway, you get the idea. He's giving you different examples. So it's good to always acknowledge others. So anyway, Phillips, excuse me. After the Phillips machine was all done, he started doing electrical engineering stuff and applying it to this new macroeconomic stuff. So in macroeconomics, the traditional idea from Keynes, remember the story, we were in the Great Depression in the 30s, we're in the ditch, we don't know how to get out. The economics of the time, there was no distinction between macro and microeconomics. In retrospect, the economists of that era were applying microeconomics to the whole economy. And Keynes just said, this is not right. So he came up with an explanation for why we're in the ditch and how to get out. And he created, along the way, what we know as macroeconomics. World War II ensues earlier in the UK. So the book came out in 36. He got sick in 37. He couldn't do anything, travel, whatever. 39, they're in the war. He's doing war stuff. So it wasn't until after World War II that all this stuff kicked into action. Phillips, if you remember the story, because he served in the military during World War II, he was able to go to school for free in the UK. He's going to study economics. He's doing the Phillips machine. That's that. So now he's got to do a dissertation, and he's thinking like an electrical engineer. And Keynes was saying, look, what you got to do is use the government to stabilize the system. So when we're in the ditch, you've got to purposely run a budget deficit to get the economy out of the ditch. It's called pump priming. So those of you who are old enough might remember these hand pumps from Little House on the Prairie, or sometimes at a state park or a national park. You had hand pumps.
We still do that in Arkansas.
Okay, so, and you prime it, you got to make a vacuum with, so you use water to create a vacuum to get water, right? So the pump priming was the government deficit spending and putting unemployed people back to work. And then they would draw a paycheck and they would spend and put more people back to work, and they draw a paycheck and they would spend, and it would raise the economy out of the ditch. And if the economy was overheating, then you run a surplus to cool the economy down. So it was stabilized. So Phillips is going, well, in electrical systems, when we try and stabilize it, we use PID. So for his doctoral work, he started trying to figure out how to model Keynes's system and then add PID control to the system. That's what the government should be doing with their budget. So right away, you should be able to see we've got the second molecule that we did, you know, an ice cube melting on hot asphalt here, right? And so this is a famous Phillips diagram here. I'm going quickly. You can read this if you want. And you can see he's trying to stabilize it with the different aspects of PID control. And here's his model. So electrical engineers love this, these engineering block diagrams, but you can see there's feedback loops, right? And so on and so forth. Well, you get the idea. All right. And he has a second paper that's pretty famous as well. He's adding to this whole story. Well, Isaac Newton came around. No, it wasn't. It's not Isaac Newton. A guy named Newton comes around. Do I remember this guy? I I don't think he's Paul Newton. Paul Newton's an SD guy at Boeing, but I don't think it's him. I think this is a different guy. I think this guy's in New Zealand. But anyway, he took Phillips's model and he said, I'm going to translate it into system dynamics for you so you can figure out what the guy was doing. So he's reproducing that diagram, some of these diagrams from Phillips's original paper, and he's quoting him and whatever. So he's showing you how to do it. How to add Phillips's PID control to a system dynamics.
Are they stabilizing output or employment in those graphs?
Oh,
What
geez,
is
I got to
the
open the
graph
papers
curve?
again. I don't remember.
I was just curious because I know the Phillips curve is like unemployment, I thought, but
Well,
then
this has nothing to do with the Phillips curve. If you remember the
Oh,
story,
okay. It's a different Phillips.
no, it's not a different Phillips. He did that too, but he did that on a rainy weekend when he had nothing else to do. And he was, I don't know what he's got. Oh, you got here stabilized. P is at the price
Okay,
level.
output. It says production, so. I
Okay,
think it's
production.
output.
All right. So Phillips, remember I said he was despondent when he passed away young because they think he had massive strokes. Series of them finally killed him. He died when he was like 63 or something. And they think it was because he was so brutalized in the POW camp for 3 years that it really impacted his health. He couldn't, he was very gaunt always. He couldn't put on weight, and he was a chain smoker because he was like post-traumatic stress disorder, whatever. So the whole POW thing, World War II, really destroyed his health and whatever. But that when he was on his deathbed, and he kind of knew he was despondent that he was going to be remembered for the Phillips curve, which is something he did on a rainy weekend when he was goofing around. He didn't even want to publish the paper. Everybody thought it was great. So they twisted his arm. He published it. It became the most cited paper in economics of the 20th century. And he said, Dad, that was like a nothing. Listen to me about PID controllers to stabilize capitalist economies. There's a way to do it. And it's blown off, not listened to. Axel Leonifed, a famous economist, famously said that the failure to incorporate Phillips's approach, he called it cybernetics. It wasn't really cybernetics, but it was the Keynesian revolution that never came off. And he said that with great sadness. Okay, go ahead, Najla.
Oh, so were you just saying, so this model this paper by Phillips was the first time that PID controllers were used in system dynamics?
In macroeconomics in the 1950s.
Oh, okay.
And then Newton said, system dynamicists can't read the engineering block diagrams, but I can. I'll translate it into its equivalent system dynamics formulation. So he translated it from German to English so us English speakers could understand it. Right? There was also an electrical engineer named Tustin who was writing about the same time and kind of doing the same thing. So it's kind of Tustin and Phillips are kind of joined at the hip as the pioneers of this.
Mm-hmm.
So Ennis, go ahead.
Yeah, so I wanted to ask, how does the feedback delays affect the PID controllers? Like the performance of the PID controller?
Well, it depends. I suppose you have to model it to see. The general thing is, the derivative control adds delay to whatever's already there. Okay. But I think it just depends on the particular thing you're controlling. If the system is has a major negative loop with that means there's delayed corrective action, and stocks create delays. That's giving you the instability to begin with. So how do the delays affect it? So delays are creating the instability to begin with, and then the various parts of the PID controller address aspects of the control system, right? But you'd have to say for any given situation, you'd have to model it, I guess. Unless, Jim, you're an electrical engineer.
Yeah, no, in electrical engineering, one of the challenges is that you you don't want a large delay because then your error is going to build up and your correction because you're changing state, right? So you've got something you're sensing where you are, what, and you want to make an actuation. You want to control something to correct for the difference. If the difference is large, then you have to make a much larger command to control something. It's like if you're driving your car and you let it drift off to the side, right? You're driving down the highway, you let it drift off to the side. To get it back into the middle, you might have to do, depending on the speed, you might have to do a large correction. It could be dangerous, right? So, so there's you gotta look at it and analyze it for, what the, how quickly you want to make updates, right? So it's same thing with your simulations, right? Your simulations can become unstable with the different DTs, right?
So, in economics, there's a large debate that's been going on for decades about rules. It's called rules versus discretion. Now, economists are not idiots. You might think they are. We are. But, they're highly educated. They do math and all this stuff. They're aware of a lot of this stuff. But traditionally, if not economists, the people who run economies, the Treasury Department, the Fed, the politicians and whatever, don't want to use rules like a PID control rule or a Taylor rule to set the federal funds market target or whatever. They want to have discretion, human discretion to decide things. So what's better? Just having a mathematical rule that says interest rates will be set based on this rule and the budget deficit or surplus will be set based on this rule, whatever, or you let the humans debate it and, and whatever. So, even though these rules work mathematically in a model, doesn't mean anybody's going to actually do them.
So Mike, like how you earlier were showing us the fitting to like you can put the mathematical model in to fit something to show the math for that particular curve, as opposed to having a table function.
Oh yeah, right.
Yeah, similarly in some control systems they'll put in if something has a long delay, right? Because it's temperature gradients, right? If you're controlling something that has temperature gradient sensitivity, those temperature takes a long time to propagate through a material, for example. So you might have to model, you might create a model of that material, so you kind of almost give a forecast of what the thing's going to be over time, right? So that helps to stabilize it, but they're harder to control if there's a long delay.
Yeah.
That's basically it.
Plus, you got to take thermodynamics now.
Yes. And it's probably knows more about that than I do. So
yeah, material science guy. Yeah.
Yeah. So
Nejla, go ahead.
Oh, I think you meant that question rhetorically, maybe, about what is better to have a model controlled economy or a human one. And I was just going to offer that with with controlling macro economies, that usually the policymakers want to be free to respond to political
100%. Yeah, they don't like rules. No.
and like if there's an election coming up, or they're going to want to make the stock market happy, or they always want to make the stock market happy, but especially if there's an election coming up, and at some point they may want to make sure asset markets or bank, what I'm saying is it's not so much the model, but it's changing the goals of the model that they want to be flexible to do. I feel like.
As a rule, whether it's the Fed or the Congress or C-suite executives at a company, they don't want to, just follow rule.
Or if we had like a better leader, in my opinion, it would be more human-centered goals, like the well-being of the people in the society, for example. Which
you could put soft variables into a system dynamics model into a whole system. That's not a problem.
Well, and of
getting people to say, like, I will relinquish
donut economics, like Kate Raworth's donut economics, like human-centered economics is a big thing now, that a lot of people are talking about. Unfortunately, not too many policymakers, I think maybe some in like New Zealand and probably the Scandinavian countries are taking seriously like economies aimed at well-being rather than growth. I mean,
Well, yeah, so a whole different conversation, but you're right. Yeah, in terms of an objective function or a multi-attribute scoring metric or whatever,
Yeah.
there's not
again,
agreement.
it's just changing the goals of the model, not so much the model. I think you still theoretically could have the same model, you know, if it's a good model of how the economy works, but it's just changing which one is your goal.
Yeah,
Like you said,
So-
what's the scoring metric? Mhm.
yeah. So, and the weights attached to the various attributes. So,
Anyway,
so
I think you meant that hypothetically, but I just thought it was a really interesting question to answer anyway.
So Phillips dies despondent that he's not listened to, and Axel Leonifid is writing in his famous book, "This is the Keynesian Revolution that never came off. You should have listened to Phillips and Tustin." But these are academics, right? They're saying, look at the math. The math works. Like oblivious to politics and all the other stuff. And it's like, if you know anything about politicians and what have you, they don't like, but as an academic exercise, it's kind of interesting. And, could you ever really pull it off? I don't know. I wouldn't try at the federal government of the United States level. I'd try maybe with a city government first or something, a town government, a little more modest scale if you're really trying to do it. Let's see if it works.
But then you have the problem that the models are completely different for like sovereign currency issuers, for example.
Yeah, and currency users versus currency issuers or whatever. But my point is, if you wanted to try using computer modeling and rules to suggest policies, like what to do with tax rates, property tax rates, whatever, you'd probably want to start small with a little test case and then go from there, rather than let's start with the federal government of the United States. Go big or go home. All right, so everybody kind of gets the story, right? I'm looking at the clock here, hopefully up to this point. So let me share again real quick here. I know we're running out of time. So where are we headed? So all that stuff is available to you. I got to put up Jay's famous market growth model. I got to put up that very first molecule for first order control, wherever that is, right over here. So I'll upload that stuff. But where we're headed, we're going to start pulling all these things together now. These ordering functions, you're going to see for the first time, start to really pull a lot of these different things together into one place. Now, ordering functions, we don't have enough time to really open that can of worms tonight, so we'll do that next time. But ordering functions are everywhere. So I think I told the story last time that when Anne was starting to meet with me for her dissertation, we met, once a week, and I said, show me your model. Where are we at? What are we trying to do here? And I said, well, that's an ordering function. You got to do that over here. And she's like, what? I go, remember in, 555, didn't really remember. And so I pulled up the Canvas site and had the older material, and she's like, oh yeah, now I remember, but she didn't make the connection, right? But ordering functions you're going to see are used all the time for all sorts of things. So in the model that Jim and I are working on for clinical trials, the people running the clinical trials are ordering patients or subjects to participate in the trial. And like a supply chain, like the beer game, they're in different stages. They're being diagnosed with the proper disease, proper in the sense that for the study. They're being informed of the study's existence, and they are convinced to apply. They're being screened, and they're admitted to the study. Then they have to actually show up, right? And the people running it, or the model, is saying, all right, how many people do I have in each of my stages here? So I get the number of subjects I need to run the study to have statistically significant results, and people are quitting and what have you. It's a classic ordering function.
The people highlighted when I was in that conference last week that they're stealing from one trial to go to another trial. There's a lot more competition than I had anticipated.
Okay, an
So
additional
there's an attractiveness function for a clinical trial itself. That
Yeah,
needs to be-
it's a very, very complex system. It doesn't necessarily seem like it is, but it is, right?
so it'll be like a market. It's a market competition structure that's going to be needed.
So it was an ordering function was used in the Battle for Moscow war game, and it's being used in a clinical trial to give you two very different uses for the generic structure. And you'll see, I don't know if you just saw it there. I have like 7 different versions of the thing, depending on what you're trying to do and what's going on and what have you. So it's quite a complex complex thing. The person who kind of did, I guess Jay did this first. It was, his model in industrial dynamics was kind of the beer game. So I guess we'll give Jay credit for doing it. Peter Senge's dissertation was kind of the system dynamics investment function, plant and equipment capital was an ordering function, and he made a lot of contributions. So there's some people will acknowledge as being the pioneers of that collection of ordering functions. But you'll see quickly, we're going to have first order control in there. We're going to have the test input molecule in there. We're going to have expectations in there. We're going to have the ordering functions. We're going to have delays, material delays in there. Like, wow, that's like 4 things we looked at in isolation are going to be drawn together now to make an ordering function. It's not an entire model of something. It's just one thing, but it uses, you speak, aha, we're building up a bigger thing by using the smaller things with which we are now familiar, right? Okay. So any questions, or I'm looking at the clock. Jeez, we've been doing this a long time. Isn't this fun? So any thoughts or questions? We have a lot of good questions this evening, so that's cool. Again, at the risk of repeating myself, all this is well and good, possibly mildly entertaining if you like system dynamics, to watch Mike open files and show you things. But in the end, I'm just lecturing to you about how to drive a car. You have to get in the car and pull out into traffic to really know these. You've got to download these molecules and look at them and goof around with them and hook them together and disentangle them and, and whatever to really understand them and begin to have them in your hip pocket to say, all right, when I'm presented with a modeling problem, am I going to stare at a white screen, paralyzed, not knowing where to begin? Or do I have somewhere to look for a beginning where somebody's done something, you've done the conceptualization thing. I got a sector here, a subsector, and in that subsector, I have an important stock and flow. Now what do? Do I have a molecule that I can use here rather than inventing something, right? That's the thought process, right? Now, sometimes you have to invent your own. That's what Suleiman was doing, right? For bringing behavioral economics into system dynamics, starting to create new molecules. But there's a whole bunch of molecules that already exist that we got to become familiar with, right? So that we have them at the ready for when you need them, right? So we'll eventually build a model that uses a lot of this stuff, and you'll see, and I'll try and talk out loud. Well, then I'm thinking this, but it's if you just watch me do it and never do it, it's you're watching a movie, a system dynamics movie. And you won't be able to do a dissertation level model, is what I'm getting at, unless you get in behind the car, behind the wheel, and pull out into traffic.
So Mike, do you for the soft variable chapter, we did that model. So I was working on that model, and I mentioned that it wasn't stable. So I had to put in like
first order control.
Yeah, but Barry must have done some balancing act with the thing that drives the instability. It's the comparator there. So do you have? I was just curious what he did. Because he must have done something.
I don't have it. I would have given it if I had it.
No, I mean, it's kind of like it's just. I would have liked to not seen it, just finish it, and then say, okay, here's what I have. What does he have? Like I was still
what
trying.
was he thinking?
I'm trying to get his version working. I can't.
I
get
don't
it.
have it, but I think maybe, I bet you that Kareem probably has it and Eb has it at IC Systems. In
Yeah, you
fact,
said there
Kareem
was-
told me they're gonna be putting up those manuals for free, the
Yeah.
PDF version, so they probably have the models. You probably would just, if you.
He must have just done
ask
some
them-
real simple formulation of that.
Oh, it's not, I haven't looked at the thing in years, but they're not complicated, but it's,
No, no, no. I meant to get it like it must have been just like for what a simple thing that was. I don't know if it was stable over the like. I don't know. I don't know what he did. So, whatever. You can make it work.
yeah, but you'll notice, I think it needs first order control for one of its outflows or whatever, ideally.
Yeah.
But
And
for whatever he was thinking or whatever the purpose was, he didn't feel, I
I mean, a
guess.
hint for people doing modeling. I have to go in as an engineer. I got to go in and you can put tables in, not table functions, but tables in to look at variables. And then you can set you can see all of the DTs. It's a different setting on the table. And I have to like look at all the values and try to guess like why it's going to where, it's just it's a math equation. So you have to,
Mhm.
you have to sit there and grind away at it. It takes a long time. If
Yeah, I think a lot of times though, particularly in the introductory Stella manuals, they just use very simple molecules. He called them atoms.
Yeah.
Other term to confuse everybody. But I don't recall him using anything terribly exotic. Every once in a while, he had something a little exotic in there when he had a counter and he had to have it reset or something. He used a funky equation with a DT in it. But generally speaking, as I recall, those manuals are so old. They're literally from like the 80s. They were
Still
very
work.
simple, basic formulations. Okay. All right. So there you go. So there again, lots to drink from the fire hose tonight. But I point you in the right direction. And it's up to you to take a look, download the stuff and goof around and acquaint yourselves with these things, and and we go from there. So when the key is when you're ready to do an original model for your PhD, you're not like a turtle on its back going, I don't know what to do. I don't know. You're raring to go.
So, Mike, was the paper were you talking about the econometrica paper for prospect theory? Is that that's the one for
Oh, kind of that. No, not for anchoring and adjustment.
anchoring and adjustment? Okay.
Yeah, prospect theory. Yeah, they're probably Kahneman and Tversky are probably most famous for that, but they did a whole bunch of stuff. But yeah, and their science paper kind of summarizes. It's a sweeping overview of like all their stuff, as I recall, up to that point in time.
There's a great book that I found that they edited. Judgment Under Uncertainty.
Yeah, well, that's the big. Yeah, this is all.
Heuristics and biases. It has a couple of interesting chapters. I have the whole book. I can give it to you.
Yeah, that's the main sort of umbrella area of this stuff is decision making in the face of uncertainty. Right? They spun the wheel. How many African nations are members of the United? Uncertain stuff. Okay. All right. Well, here you go. Chew on that for a week. So I'll upload those files, and then next week I guess we'll look at ordering functions. Booyah. All right.
Yep.
All right. We'll see ya. Take care, everybody. Bye-bye.
So,
Thank
Mike,
you.
just a quick question before you jump off.
Yep.
So if you need anything more for Rob, just let me know and I'll try to like crank it out really quickly. I don't know if you want to just scan the thing I sent you.
Yeah, no, what I'll do is I'll give it to Rob and go, dude, is this okay or what? And let him.
So I'll let him.
He's the one
yeah, okay.
For the paper trail thing, that's different from what we need for the dissertation proposal. That's
No, I know. I can work on that. I'll work on that. I'm gonna lift and reuse and repurpose some of the stuff that I wrote because it sets I kind of just described the problem space.
No, I
And
know.
then
What I'm saying,
yeah.
what I'm saying is my opinion doesn't mean shit when it comes to the thing for CGSR. That's a
Well, I just-
CGSR/Rob thing. So I need to run it by him and say, dude, is this for Fred and you sufficient to get CGSR to do whatever they got to do. And when he tells me it's fine or whatever, then I'll circle back to you. But since I didn't talk to CGSR, I don't know and he's never said specific. All he did
Yeah.
was have your guys do like these, and he sent me the examples that I sent.
Yeah.
to
Fred,
you.
again, I'll probably provide Fred this feedback. He's a brilliant, and he's making it harder on himself. He's trying to include too many domain areas. You can touch upon them, but you really can't do justice. I'm even I'm going to be using some data science because that's just, I mentioned that. I mentioned like insurance, understanding the insurance industry a little bit. So I kind of modeled a little bit after him, but then I'm still thinking that I don't, it's sort of like it doesn't matter for CGSR, but it matters more for the dissertation proposal, not to promise too much stuff. Because people start asking me questions about stuff that when I decided, hey, that's not really relevant. It's not as relevant as I thought it was at the time I formed this thing. I might paint myself into a corner.
Ask a question, answer a question. And when you answer,
Yeah, I wrote three ideas. I'm gonna have to play with them for my papers. Here's the questions. This is the question. Here's the question I want to answer, and here's how I'm gonna approach it. I want to not can't, and I wrote them before like yes nos, but I rewrote them so that they're
yeah, yes, I remember when you
that was good feedback. That was good feedback.
Yeah, so you ask a question, answer the question, and when you answer it, you're a lawyer trying to convince a jury. So you tell a narrative in the paper, each paper,
Yeah.
and you bring evidence to support your narrative, right? And that's how the lawyer convinces the jury to find your client innocent. You don't just say he never did it. You guys say he never did it because here is a timestamp photo of him in another state when the crime happened. That's evidence that supports your narrative, right?
Right.
So that's all you're doing. So if Fred is, we got to like reel him in, like, dude, this is not your Winston Churchill memoirs when you're 80 years old, recounting your entire life. It's 3 questions you're going to ask and answer scientifically, and get your
the 3 questions I wrote in the paper 1, paper 2, paper 3 for CGSR to just kind of like say, hey, I'm going to be doing something that's interdisciplinary. I need to do more than one department. I don't think they're not perfect yet, so I need to noodle on those and then build up a description of how I'm going to
So
get there.
perfect is not necessary for CGSR, right?
No, I know. I'm just saying that, but I'm saying,
Perfect quotation fingers will be necessary for the proposal, so that when everybody signs off on it, you have a little contract with the committee that says you're doing these
Yeah.
things. Now you can modify the contract. We did that with Anne. She started with a 3-paper dissertation. She ended up with a 2-paper dissertation, but it was with the consent of everyone involved. I had to shop it around and say, realistically, she only needs to do 2, because it's essentially the same work as 3, but it's just packaged a little differently. What do you think? And everybody's like, yeah, we agree with that. So we modified the agreement. But
yeah, I think, like I said, the first paper is the modernization of a well-known healthcare system simulation model for studying the decline in innovation capital, right? So that's my first paper title. But then the question to answer in the paper, this is the way Fred did. I think this is better because the title shouldn't be the question. And I don't think the first one, I don't like the question as much, but I'll work on that. The second and third one papers, they're just proposed papers. You and I are going to have to talk about it over the next month. But I got to scramble because I want to get this done before maybe we have a version in a week because I have a lot of material to write up. But again, the story is, I think it's a relatively straightforward proposal. I mean, I know I need to spoon feed some of the members of the.
you don't want to make it overly long. If a committee member, you're trying to, because remember, none of us, meaning professors, have to be on any dissertation committee. It's purely a voluntary.
Yeah.
Maybe we'll get our name on a paper out of it for if we contribute, or we're just trying to be a nice guy or something like that. But imagine you're a prof and you're busy as shit. And now somebody approaches you and you say, well, and they dump this 109-page proposal on your desk, let alone the dissertation. You're
Just
like,
this description, the objective, no, the background section I have is already 4 or 5 pages. I'm thinking maybe a 10, 15 page proposal.
I like to say 10 pages. There's no rule that says it must be
Yeah,
10.
I'm saying this just a simple background that I did for CGSR, which I want to repurpose some of it. It does help, but I need to even put some more simplistic up front material.
What I would always do,
I'm already at 4 pages.
what I would always do, so you say 2 birds with 1 stone. So
Yeah.
I need to do a literature review for each paper. In other words, here's the question I'm posing. Here's why it's an important question. Here's what others have done to try and answer the question. That's your literature review. Then here's what I'm going to do that takes the next step. So I've outlined for you.
You're recording all this still. Sorry.